So for quiz 1, you were given 2 problems under crystallization, industrial crystallization. And these are the problems. I'll read it first. You can take a screenshot. And then I'll show to you the solution. So for number 1, you are given a 20 weight percent solution of sodium sulfate at 200 degrees Fahrenheit, which is pumped continuously to a vacuum crystallizer from which the magma is pumped at 60 degrees Fahrenheit. So you are asked to calculate for this one the mass in pounds of the liquor in the magma. And for letter B, you are asked to determine the percentage by which, by weight rather, crystals in the magma. So this is the handwriting of your classmate. Percentage by weight crystals in the magma. And C, percentage of sodium sulfate in the feed recovered. So how much of the sodium sulfate originally present in the feed was recovered. Okay, that's for number 1. So you may take a screenshot of this. Then I will read as well number 2 so I can cover the solutions after this. Okay, so I'll just read number 2. In the case of number 2, you're given a Swenson-Walker crystallizer which is used to produce 1 ton per hour of copperas, iron 2 sulfate, or ferrosulfate heptahydrate crystals. Now, the saturated solution at 120 degrees Fahrenheit. So the saturated solution of copperas is introduced into your crystallizer at 120 degrees Fahrenheit. The steam, or rather the stream, this would be the stream leaving the crystallizer, is at 80 degrees Fahrenheit. Cooling water enters the crystallizer gas at 60 degrees Fahrenheit and leaves at 70 degrees Fahrenheit. It may be assumed that your U is 35 BTU per hour per feet squared per degree Fahrenheit. And there is 3.5 square feet of cooling surface for every foot of crystallizer length. Okay, we need this in determining how many lengths of this particular crystallizer is needed for this job. So the CP of the feed is 0.7 BTU per pound degree Fahrenheit. The heat of solution is 4,400 calories per gram mole. Actually, this is gram mole copperas. Solubility at 120 degrees Fahrenheit is 140 parts per 100 excess water. 100 parts excess water, that is. So when you see parts, it means weight. Okay, weight fraction or weight percent. Depends. Basta if the units is parts, it refers to the weight. Now, solubility at 80 degrees Fahrenheit is 76 parts per 100 parts excess water. Now, you are asked to answer 4 questions in this case. So, what is the cooling water required? And for B, what is the number of crystallizer sections to be used if 1 unit is 10 feet in length? So, this is the condition. How much feed in pound mass per hour will produce the amount of crystal that is indicated? So 1 ton per hour in this case. And D, what is the total heat removed in the process? Actually, the D and the A are related. So you cannot answer the A without knowing the D. Okay? You can even answer the D and the A without knowing the C. So they are all dependent actually on C. Okay, so you may take a screenshot of this problem. So later on, if you're going to see the solution already, you have something to refer to. So this is for number 2, problem number 2. And this is for problem number 1. Okay. I hope you're done taking already the screenshot of this. I will close this now unless somebody would tell me that they were not yet done taking a screenshot. So this are the 2 problems given to you under crystallization. Quiz 1. So I'll close it now. And I'll share a different sheet. That would be for the solution of this one. I hope you could see my handwriting. You can see the solutions already. For number 1, I am only showing number 1 in here. So for number 1, if you have the problem with you, you can refer to that. So this is the temperature of the feed. This is the weight percent sodium sulfate. And this is your crystallizer, which is going to produce the magma, which is part liquor and part crystal. So your magma is composed of your liquor and your crystals. And your crystal is sodium sulfate decahydrate. The solubility is 21.778 grams per 100 grams water. So this is at 60 degrees Fahrenheit. So these are your given information for number 1. And these are the required information. So the liquor in pounds, your percentage weight crystals in the magma, so M is magma, and percentage sodium sulfate recovered from the feed. Okay, we'll make it bigger so I can see as well. So in this problem, you need to have a basis of feed because you don't know the feed that was used to produce the crystals. Now, you have to remember, class, that if neither the feed nor the crystal is given, you really have to make a basis because you cannot know any of the two unless you make a basis. So in this problem, you're not given the crystals produced, you're not given the feed that is being used in producing the said crystal. So you need to have a basis. In that case, your basis here would be on the feed. But it need not be 100 pounds. We're just using 100 pounds for ease because we're dealing with percentages here. So you can have 1 pound or 100 pounds, but it has to be in pounds because your unknown here, the liquor is asked in pounds. So that should be in pounds. So your basis should be in pound mass or pound weight. If you do overall material balance, so your feed is equated to the sum of the liquor and the crystal. So this is your assumed your basis, which is 100 for the feed. So you have initially one equation that relates the crystal produced to the amount of liquor in which it is on it, which is part of it which is together with it, rather, not part of it, together with it in your magma. Okay, so this is your equation. Then if you make sodium sulfate balance, so the sodium sulfate balance, of course, will be the sodium sulfate coming from the feed. So that's 20%. And then this is your 100-pound feed. And in here, you're using the molecular weights. Okay, you have, in this case, the 21.778 grams here was used based on the solubility that is given in the problem. So the solubility of your crystal is 21.778 grams per 100 grams water. Solubility is otherwise in terms of concentration. So in some problems, when you speak of solubility, it's also referring to concentration. So in this case, since you're given 21.778 grams per 100 grams water, you can get here the percentage by weight of your sodium sulfate in the magma. So in the liquor, rather, that is given. So you have 21 here, 0.778. You have 100 water for that, and you have 21.778. So this is the percentage by weight of your sodium sulfate in the liquor. As for the sodium sulfate in the crystal, you are not given any concentration anymore in the crystal. You can work on it based on molecular weights. So there's a sample problem in Gen Kuplis that if you're not given concentrations, especially in the crystal, you can use the molecular weights of the anhydrous and the hydrated crystal. So in here, you don't have water yet. So the molecular weight of sodium sulfate, not hydrated, now this time divided by the molecular weight of dehydrated sodium sulfate. So this is still in itself the weight percent of sodium sulfate in your crystal. So what you're adding here actually is the sodium sulfate present in your liquor and the sodium sulfate present in your crystal. Okay, so again, when you intend to determine the amount of your solute, in this case sodium sulfate, in your liquor, that would be using the solubility that is given in the problem. Either the solubility, the term is solubility, or you can also read the term concentration. So it's just the same thing. So in that case, you have now an equation which relates also L and C. So if you work out equation 1 together with this, you'll be able to find right away the liquor. So your answer here, actually, the 91.88 pound is per 100 pounds of feed, which you use as the basis. So if you used only 1 pound of feed in here, your answer would be 0.9188 pounds. Because this 91.88, you need to divide by 100. So for every pound, this means that for every pound of feed that you process, this much of liquor is produced, or is present rather, in your magma. Okay, that's the first question here. The pound of liquor in the magma. Now, the next is you're asked to determine the percentage by weight C in the magma. How much of the crystals is present in the magma? So before you can answer that, of course, you need to know the crystal. So you go back to this equation, substituting the value of the 91.88, because that's the one that we got for the basis that we used. You have the C. This is your C. So you get the percentage of the crystal in the magma, which is the C over the C plus the L. Actually, this is 100 times 100. So the percentage by weight crystals present in the magma is just 8.12, or the 100 minus the 91.88. Now, as for recovery, so you use material balance for recovery. How much of the sodium sulfate rather present in the feed was recovered in the crystals? So your denominator then must be the total amount of sodium sulfate present in the feed, and how much of the sodium sulfate is present in the crystals. So you have your C, your crystals here, your 8.12, and you have the 0.44. So the 0.44 is the ratio of the molecular weight of the anhydrous and the hydrated sodium sulfate. That's the amount of sodium sulfate that is present in your crystals. Remember, your crystals does not have only sodium sulfate. It has also water. So you have to multiply the 8.12 by 0.44. So your percentage recovery is 17.86 in this case for this problem. So it doesn't matter what basis you use here, you will still be getting the same answer here in the percentage recovery. Actually, the very essence of this problem is determining the percentage recovery, regardless of the feed that you process. So if you have 1 ton of feed per hour, this will still be your percentage recovery. If you just have like 100 kilo processed in an hour, this would still be your percentage recovery. So this is your solution for number 1. Do you have any question here?
Miss?
Yes.
Miss, ma-zoom out, miss, so we can take a screenshot.
Okay. Sorry. Kaya hindi nyo gali makuha tanan. Hindi ko makita abi kung gamay. Wait, ha? Or, sige, para hindi budlay sa inyo, just take the screenshot of the problem. Actually, I already have the pictures of the problem. I'll share all the files of the screenshot na lang later para mas klaro. Okay, may-ari man ko there are 20 of this, then I'll share it in Canvas na lang para hindi ka mo sagi kuha. Okay?
Thank you, miss.
Sige, tingubon ko na lang together with the recording. Sige. So, any question here before I close this one? Okay, so none. I'll close this now. I'll share a different file. So the second thing would be, of course, the solution to number 2, which talks about the Swenson-Walker crystallizer. Like this. In the case of your Swenson-Walker crystallizer, okay, I hope you can see it. That's very big. So your feed is at 120 degrees Fahrenheit, and this is the temperature of the magma as it leaves the crystallizer, the process feed that is. Your crystal is in the form of ferrous sulfate heptahydrate. And in this case, the problem gave you the amount of crystals produced. So in this case, you don't need to have a basis because you can now connect your feed to this mass of crystal that was produced. So 1 ton per hour, I just place here 2,000 pounds because I need the unit converted to pounds to make sure that all my units will agree later. Okay. Now, your cooling water, the CW, enters at 60 and lives at 70. And these are the rest of the information given in the problem. Okay, you have your U, you have your A. So your area is 3.5 square feet per foot of crystallizer length. The CP of the feed is this. The heat of crystallization is this. Calorie per mole Popera, solubility. Okay. At the two temperatures, 120 and 80, or in short, the concentration at 120 and at 80 degrees Fahrenheit. The problem asks you for the cooling water in gallons per minute. So you'll be needing here the density of water because your cooling water in here is in volume per unit time. Then letter B is asking how many crystallizer sections would you need if a unit is 10 feet long? Okay. The manner in which the problem is constructed does not necessarily have to be followed when you solve it because the feed is asked here on that is the third requirement. It should have been the first thing determined. And of course, the Q was even asked last. So these two are needed in here, even in here. Okay, so what you do, you just solve as you go along and then just box your answer or just pick out the answer if it's multiple choice as you get to determine them. So you do again material balance. You won't get wrong if you start always with the material balance. Overall material balance is F equal to L plus C, just like number 1, and your C is 2,000. So the units I'm using here is pounds per hour. So your liquor in terms of the feed is F minus 2,000. If you do solid balance, it's patterned after this one only that you're going to multiply your streams here by their weight fraction. Okay, you have this one. So you have for the feed, it says here it's 140 parts of your ferrous sulfate per 100 parts water. So what you do, you have the 140 in here. You still have the 140 in here and the 100 water. So this is the weight percent of ferrous sulfate present in the feed. Now for your L times XL, I already changed the F, or rather the L to F minus 2,000. So I only get to determine right away the F. So I need not have another separate line. Then I use the concentration that is given at 80 degrees Fahrenheit, just like also number 1. You use the concentration of the magma at the indicated temperature, which is 80 in this case. So 74 parts ferrous sulfate per 100 parts water. So you have 74 here, 174. Now for the crystals, you have already 2,000 pounds per hour. So you write here 2,000 pounds. So your feed is this, 7,278.48 pounds per hour. The reason why you need to determine the feed first, actually you need not start with this, but you'll know that you'll go back to material balance later on when you start to write your working equations. You need the feed in the determination of the heat that needs to be removed from your solution. That way you'll get to form crystals. So your total heat removed is the Q needed for cooling and the Q needed for crystallization. We have a similar problem on this, I think, a sample problem that was discussed to you. So for the Q for cooling, it's patterned after the generic formula MCP delta T. So how much heat is needed to cool off your feed to the indicated temperature here? From 120 to 80. So 120 to 80. So you have F CPF delta T. So you have it here substituted, the temperatures. And for your heat of crystallization, your heat of crystallization is per mole coperas. So when I first saw it, actually I got a mistake because I thought it's gram coperas, but it's mole per mole coperas. So you have to convert the grams to mole using molecular weights. So in this case, you have 4,400 calories mole coperas. We convert the calories to kilocalories, I think, because this is the conversion I used to convert it to BTU. Then I have the pound here. Where did I get the pound? So this is already BTU. And I have the conversion of the grams to pounds. Why? Because I have the original amount that is given in my crystals is 2,000 pounds per hour crystals. So I need that converted into pounds. That way I can use a molecular weight expressed in terms of grams per mole. So it's just dimensional analysis. So if I substitute the amount of my crystals, which is 2,000 pounds per hour, it will not agree with the unit here that is given for the heat of crystallization, which is calorie per mole. The calorie I have already addressed by this conversion, but the per mole I will not be able to address if I stick to the pounds here. So convert the pounds to grams, then use a molecular weight, which is of course in grams per mole. This one is the molecular weight of the coperas here. So this is the molecular weight. Where is it? This one, the 277.908. So your Q total in this case is 260,881.08 BTU per pound. And you get to answer the third and the last question first in this case. Once you have this Q, I think you know what to do. You need to equate it to the amount of water that is needed to, of course, produce the crystal for the cooling of your solution here, your feed. Okay? Now, before I go to the second part of the solution, we are done with this F and this Q total. Do you have any question? So there's none. So I'll close this one now. Okay. So this is your Q total, which is equated to MCP delta T for your cooling water. So our answer a while ago in the Q total was equated to the mass of the cooling water times the CP in BTU per pound degree Fahrenheit. So this is the CP. And you have the delta T. The delta T for your cooling water. So final is 70 and initial is 60. So you have the mass of the cooling water in pounds per hour. So this is the mass flow rate. Convert the hour to minutes. So you have it in pounds per minute. However, the problem requires you to get the requirement in terms of volume per unit time. So you need to have the density of water. So your answer here should be divided by the density and just simply convert the cubic feet unit of volume to gallons. So this is the volumetric flow rate of your cooling water. This is the first requirement. The last requirement is the number of crystallizer sections. So that will be using this also very generic formula in terms of heat transfer. Q equal to UA delta T. So in this case, though the problem is not specific as to what type of orientation do we have, is it countercurrent or co-current in terms of our cooling medium and the feed, we just assume that right away it's countercurrent because it's more efficient as discovered and as discussed with you in heat transfer. So you use determine the delta T log mean in this case. So you will have these two temperature differences, 120 minus 70 minus 80 minus 60. The difference of these two, you have 50. The difference of these two, you have 20. So your delta T log mean is 32.74 degree Fahrenheit. So from in here, you just substitute the Q, you substitute the delta T log mean, you substitute the U that is given in the problem, you'll be able to get an A, which is 227.66. Now, as to the number of crystallizer section, you have to use the information in the problem that for every 3.5 square, for every foot length of crystallizer, you have this much of area available. So this 227.66, you divide by 3.5 feet squared per foot length of crystallizer. So you have the length of crystallizer. Now you divide it by 10 feet because what is readily available probably from the supplier is 10 feet long. So how many sections of this 10-foot length of crystallizer, which has an available area of 3.5 per foot? So this would be the number that you'll be getting, 6.5. So since you're buying something, so number of crystallizer sections, hindi man ka pwede ka answer, there are 6.5 kay sections na siya. So meaning, it's ready-made already. You cannot answer 6 because you will not have this area. So you will have lesser area if you're just going to use 6 sections. So you have to use 7 sections in this case. So I've noticed your answers are raw answers. In this case, you have to round it off to the nearest whole number because when you buy these sections, as I've said, from suppliers, they are bought per length. So the answer should be 7. Although I saw that in terms of principle, there were some who got this answer, but did not answer the whole number answer in here. So your answer should be 7. Okay? Okay, nga i-divide iha sa 10. I-divide siya sa 10 because it's given in the problem that for every one section is 10 feet in length. One section is 10 feet in length, and for every foot length of this section, you have this much of area, 3.5 square feet. This one is given, this is a given information in the problem. One section is 10 feet long. Yes, Bob. Miski 6.1 lang na siya ma-7 kagid. Kaya kung 6 na yung answer mo, hindi mo makuha ang area mo nga needed for heat transfer. Your Q total will not be addressed if you use a lesser area. So it's not the case nga round off lang kita kung 5 and greater than 5. Even if it's just 6.1, you should answer 7. Okay, any question here before we go to quiz 2? Okay, sige, i-close ko ha. Okay, we go to quiz 2. We'll read first quiz 2. We'll read the problems in quiz 2. The problems in quiz 2 are taken from John Cooklis. They are the raw problems I took from there because if you recall, you were asked to listen to just the recordings of this. So I cannot deviate much knowing that you relied on what you listened to. So I just measured the fundamental principles that were discussed in the sample problems that were as well covered in the discussion. I just changed some of the information. So I'll now share my screen. I gave you 3 problems for quiz 2, but you are to choose only 2. So some chose 1 and 3, some choose 2 and 3, but there's really one problem that's just a giveaway, which is really very, very short in terms of its solution. But anyways, this is the problem where number 1 was taken from. You have a diffusion of ethanol. In this case, ethanol is A and water is B. So ethanol is diffusing through B. Now, it's in the form of a stagnant film, 2.0 mm thick at 293 Kelvin, and it is in contact at one surface with an organic solvent, which is ethanol, in which rather ethanol is soluble. So it's in contact with an organic solvent, not specified. Ethanol is soluble, but water is not. So in this case, your NB, your flux for B, which is water, is 0 because anyway, it's not diffusing through this particular organic solvent. At point 1, you're given the concentration of ethanol, which is 16.8 weight%, and the solution density. In this case, I changed, I think, the weight percentage here. And the same thing with the weight, with the thickness of the film, I think I changed also. At point 2, I also changed the concentration of ethanol, but the densities I kept because, of course, it's the density of ethanol. Now, you're given the diffusivity of ethanol, which is 0.740 times 10 raised to negative 9 square meter per second. So you are to determine the N sub A, which is the steady state flux. Okay, that's for number 1. So you may take a screenshot of this just for your own use when we discuss the problem solution, because I just discuss all solutions together and I will read all the problems as well in one setting. So I need not go back to each of these problems again. So that's your number 1. I'll close this now. So we have number 2 here. Now this one, you have diffusion of a gas to neoprene membrane, or the diffusion of a gas to a membrane. In this case, it's neoprene. So your gas in here is hydrogen at 17 degrees Celsius at this particular partial pressure, 0.01 atm, and it's diffusing through a membrane of vulcanized neoprene rubber. The thickness is 0.5 mm thick. So the pressure of H2 on either side of the neoprene is 0. So calculate again the steady state flux that has something to do with Na. That's your Na, assuming that the only resistance to diffusion is in the membrane itself. So the only thing that offers resistance to the diffusion of H2 is the membrane itself. The solubility S of H2 gas in neoprene at 17 degrees Celsius is 0.051 cubic meter. This is at standard temperature pressure of 0 degrees Celsius and 1 atm. So the unit for the solubility is 0.051 cubic meter per cubic meter solid. The neoprene rubber, that is per atm. And you're given as well the diffusivity. So I think what I changed in here is the thickness. I think it's just the thickness that I've changed in here. Okay, that's number 2. We'll go to number 3. This time, it has something to do with the evaporation of naphthalene. Okay. Naphthalene, a sphere of naphthalene having a radius of 2.0 mm is suspended in a large volume of still air. The diffusion of naphthalene that has evaporated in air at 318 Kelvin and 101,325 Pascal. So the surface temperature of naphthalene can be assumed to be at 318, same as that of the air in which it is suspended. And its vapor pressure at the same temperature is 0.555 millimeters mercury. You're given the diffusivity in here of naphthalene in air. You are to calculate the rate of evaporation of naphthalene from the surface. It's still Na. Okay? Still asking for Na. So this is under the topic of diffusion. So this is your first of the two quizzes in one meeting. But in this case, you are given the leeway to choose from any of the three numbers. You need only to solve two. Okay, so this is the third. I'll close this one now and I'll share to you the solution. So this is the solution for number one. I paste in here all the information, the diffusivity, the thickness from 2 mm, I changed it to 3 in the given problem. So that's the only thing I changed, together with the weight percentages of ethanol in 0.1 and in 0.2. Okay. So 3 mm, you have the weight percent of ethanol in 0.1, and in 0.2, you have the same densities in here. You are after the steady state flux. As per formula class, in the case of this problem concerning steady state flux or concerning mass transfer, specifically in diffusion, I suggest that you always start with writing the formula that you will use in solving the problem. That way, from the formula, you will be guided on what you need to determine first. And when things are already in place, you can go back to the formula and substitute. So this 46.05 and 18.02 are the molecular weights of ethanol and water, A and B. And using these molecular weights of ethanol and water, we get to find the mole fraction of ethanol and in points A, or in points 1 and 2. So this is for A. This is the mole fraction of A, ethanol. So you use the percentage here. So you see 0.2. So this is the subscript class. This is the mole fraction of ethanol A in 0.2 or at 0.2. So you have 8.8, you divide it by the molecular weight of ethanol, you have the same thing in the denominator. And since you have 8.8 ethanol, it follows that your water is 91.2. You just subtract your 8.8 from 100. So these weights are divided by the formulas to give you the mole fraction of ethanol at 0.2. You do the same for water. So once you have already the mole fraction of ethanol, all you have to do is subtract it from 1. That would be for water. The same principle you will use for determining the mole fraction of ethanol at 0.1. So you use the percentage 18.8, you subtract it from 100, that would be your water. You divide the 18.8 and the 81.2 by the molecular weights of ethanol and water. So you will have the mole fraction of ethanol at 0.1. The mole fraction of water at 0.1 is this answer of yours subtracted from 1. So you'll now have the M1 and the M2 that you'll be needing in this formula for the average concentration, C subscript AB. So you have the densities that you have here in points 1 and 2 divided by M1 and M2. So how do you get M1 and M2? So this is the mass, of course, divided by the mole fractions of these two. So you have, in the case of at point 2, you have 0.1, where is that point? 1911 and 5.01. So this is kilogram mole. Okay, wait, class ha. Kilogram per kilogram mole. So this is the molecular weight of the thing that is present in point 2. I did not place here the point 1911. Where did I get this one? Wait, class. Mole. Okay. So you have, if you have your calculators with you, you can have 8.8. So 8.8 divided by 46.05. Can you check, and you'll have 0.1911, and 91.2 divided by 18.02, that would be this one. Okay, dire wala ko siya ginsolve, so dire ko ginbutang. Okay, and then for 0.1, you use also that of 0.1. So this one, 18.8 divided by 46.05, I think that's your 0.4083. And your 81, what's that? Your 81.2 divided by 18.02, that would be your 4.5061. So this is the molecular weight actually of your mixture at 0.2 already. This is the molecular weight of your mixture in 0.1. You use these molecular weights in points 1 and 2 as a divisor for density, so that you will have the average concentration. So you're taking actually the concentration at 0.1 and 0.2 and taking the average. So you have this one. You use the densities that are given here, these two densities. You divide it by the molecular weights at points 1 and 2. And the sum you divide by 2. So this is it. The reason why you're doing this is because you need it in here in the formula. You have that one there in the formula. The XA1 and the XA2, we have it here already. Okay, so you need it in the formula. So your XBM is the average of XB1 and XB2. So we have determined it here. So you just get the average. So this is it. So from 1, since you have everything already determined, you go back here and substitute. So you substitute everything in 1. Your Z sub 2 and Z sub 1 is the thickness of the stagnant film, which is 3 mm. Originally it's 2 mm. I changed it to 3. So you just change it to 3 here. And this is your steady state flux. This is formula based. The problem is formula based. So the reason why you have to write the formula first, that way you'll be guided what you need to determine based on the formula that you are using. This is it for those who solve number 1. So this is your solution. Quite lengthy compared to the solution, I think, of number 3. Number 3 is short, or is it number 2? I forgot. It's very short. Any question here? Sige. We'll go to the second problem. Okay, so this is in the case of your hydrogen diffusing through vulcanized neoprene rubber. Okay, the thickness is 0.7 mm. I changed it to 0.7. Originally, I think it's 0.5 mm. You are given this solubility of hydrogen in your solid neoprene rubber per pressure, okay? Per unit pressure here, ATM, and this is your diffusivity. Your formula is this one. In the case of gas diffusing through a solid, your concentration here is the solubility divided by 22.414 times PA1. Pressure at this side. You substitute what is given in the problem and the pressure. If you're wondering what is this 22.414, I'm not so sure if it was covered there in Genku, please. It's a fixed number that is written in the formula. So when you see the formula for CA1, in cases like this, it has already this constant, which is 22.414. So what is that 22.414 that will help you determine the concentration at this side of your neoprene rubber when your H2 starts to diffuse from this side to this side, from 0.1 to 0.2. So I place it here. This 22.414 cubic meter per kilogram mole is its set unit, is the molar volume of any ideal gas measured at standard temperature and pressure. So volume of any ideal gas, even if H2 is not ideal, we need to assume that it's ideal. Otherwise, we can't use this particular formula. So you have already CA1, and CA1 is needed in here. You have CA1 and CA2 automatically at this side is already 0. Okay? It's always 0 on this side in here for the concentration of the gas after it has already completely passed through the diffused through the solid. So it's always 0 in here. Please read again that part in Genku, please, or listen to the recording. So you have to substitute DAB, your concentration here, this one, and the thickness. And this is already the answer. I think this is the shortest of the 3 problem. Though since you are given the choice to choose, all problems will have the same points, okay? Regardless whether it will be short or long in terms of solution. Any questions here? Sige, we'll close now and we'll have the last. So this is in the case of the sublimation of naphthalene balls suspended in air. So the diffusion is due to evaporation of or sublimation of naphthalene. Now this is the radius, this is the temperature, this is the pressure, and this is the, I think, the partial pressure of naphthalene, 0.555 millimeters mercury, and this is the diffusivity at the temperature of 318 Kelvin. The same thing. So you're asked for the flux. This is your formula to use. So when we deal with gases class, diffusion of gases, you use the formula which has the partial pressures. Chooses the partial pressures. You have partial pressure at 0.1, partial pressure at 0.2. This one is the average. And you have R1, that's the radius, because your solid is spherical. RT is the universal gas constant and the temperature absolute, respectively. And there's a specific value for the R that you are to use if you're dealing with SI units. I'll show it to you later. This one is the total pressure and this one is the diffusivity. So that's your formula. So all you have to do is make sure that you know what to substitute in your formula and you have everything there ready to be substituted. Just like number 2, when the thing that is diffusing to something has already fully diffused through the the thing that it's going to diffuse to, its pressure is 0. Normally at 0.2, its pressure is 0 or its concentration is 0. Now in here, meaning you are to substitute 0. In here, you are to substitute this one. You get the average. But what is PB1? So PB1 is your total pressure minus the partial pressure of naphthalene. Okay, so that would be 101,251. The B in here is the air, because your A is your naphthalene that has sublimed. Your B is your air. So you need to know PB1 and P subscript B2. So you have the partial pressures of naphthalene subtracted from the total pressure. You have to get the P sub B1 and the P sub B2. So your answer here, you subtract from the total pressure. Your partial pressure here is subtracted from the total. So you have this and get the average. That's it. And then you substitute. You substitute to the formula. You have here your diffusivity, you have your total pressure, you have your partial pressure difference of A at 0.1 and 2. The R that you will use is A314, cubic meter, Pascal, kilogram mole per Kelvin, per kilogram mole rather per Kelvin. You have the temperature, and you have here the P sub BM, the average partial pressure of air in points 1 and 2. Okay, and this is your answer. So a quiz that could be answered actually, although damo ang box ang ginstudihan. Miss, for varying cross-sectional area, there are two equations. How do we know which one is to use? Varying cross-sectional area. Okay. Let me check. Do you have your book there, Bob? Can you refer to me to a particular equation so I will know which equation you're referring to?
Wait, Miss, may tangan ko.
Sige, sige. I'll look also in here. Check command.
6 point.
Okay. I see it already. Your varying diffusion to varying cross-sectional area. So you have 6.2-27. One equation is that. And you have another one in here. Your area is your surface area. So I suggest that for the rest, if you have your soft copy of the book, you also open it. The formula is actually NA equal to an A bar over A, where A is the surface area. So that is why in 6.2-28, you have 4 pi r squared. It's the surface area. So it's the same thing that you have in here. Your NA, in this case, was equated to the diffusion expression for flux, which is negative of the diffusivity times dPA RT 1 minus PA over PDR. In this case, you're asking me, ano ginapamangkot mo, Bob? Kundi
Ari din Miss ang 30, ang 30, ang amo na siya Miss ang equation gi-derive na ang nakuha yung equation is ang 32. Then naghambal siya nga if si gas dilute enough, it can be simplified into equation 33.
33.
Para sa aton Miss nga situation subong do ka kay since gamay-gamay man Miss ang partial pressure ni it can be considered nga dilute sa. So why in this case did we use 32?
Aging gamit ko nga formula iyan ni 32.
Yes, Miss.
Actually, ang iniimo nga 6.2-33, Bob, it's a simplifying equation which you can use for dilute, just like what you said, for dilute solutions of the thing that is diffusing and to where it is diffusing to. It's a simplified equation. Amo ning equation yung gamit mo, but it's not wrong when you use 6.2-32. Wala man siya nagamba nga hindi mo ni siya pwede magamit kung dilute. But you are given a more simplified equation if it's dilute, and that's your 6.2-33. So, if you're asking me which of the two equations, kung multiple choice Bob, kundi sa duwa ka equation ang maghatag sa imo sa answer nga available sa choices mo kay hindi man isala ang 6.2-32. Simplified version niya si 6.2-33.
Sige, Miss. Trial and error lang naman, Miss.
Although kung ako estudyante, kung kabalo na ko nga dilute, dirigi ko makadto sa 6.2-33. The same thing with problems sa naton nga if you recall sa karon na lang sa aton nga gas absorption kay kadamo sang method sang pag-determine sang tower height. So it's the same thing with that. May ara nga mga equations nga available kung dilute siya. But it doesn't mean nga kung dilute siya ginsolve mo siya sa original gid nga equation nga fundamental masala imo answer. Galing amulan na if you're provided with choices, pangitaon mo gito sa choices kundiin ang imo nga answer na walapit. But in your case, ang question mo diin sa duha ang gamiton mo. To start with the simplified equation. Kung hindi mo da makita imo answer, di wala ka choice. Balik ka sa fundamental kung di na naghalin si simplified.
Sige, Miss. Thank you.
Okay. Sige. Sino pa may question? Base ang iban sa inyo, ang gigamit, you used a different formula here, it's okay. Doesn't mean nga amo lang ni siya answer. Kaya may simplified ta nga form. Galing kay amo, mahilig ako mag-solve nga based sa kung anong fundamental equation. Pero if you answered based on the simplified formula, it's still correct. Okay? May pamangkot? Sige. So we go to quiz 3. For quiz 3, I'll show to you the problems again, all taken from the book. So we're now more concerned with mass transfer on solid surfaces or from certain geometries, ano geometry ang specify sa problem. So in this case, we have mass transfer from a flat plate. So you're given only two problems in quiz 3. So in this case, you're given a large volume of pure water at 26.1 degrees Celsius flowing parallel to a flat plate of solid benzoic acid, the length of which is 0.244 meters in the direction of flow. So your pure water is going parallel to the flat plate with this length. The water velocity is 0.061 meters per second. You're given the solubility here of benzoic acid and its diffusivity. Calculate the mass transfer coefficient K sub L and the flux NA. Okay? That's the first. I may have modified some of the given here. You will see it later in the solution. The second, so nakat ini siya because it's written at the lower part of the textbook. So the continuation is in the other one. So this one is mass transfer inside the tube. So your geometry here is not a flat surface, but a tube. So this time, your tube is coated with naphthalene and has an inside diameter of 20 mm and a length of 1.10 meters. Air at 318 Kelvin at an average pressure of 101.3 kilopascal is, I think, flowing through inside the tube. So I'll close this one. I'll go to the next part. Because not that one. So it flows through this tube or pipe at a velocity of 0.8 80 meters per second. So air is flowing inside the tube coated with naphthalene. Assuming that the absolute pressure remains essentially constant, calculate the concentration of naphthalene in the exit air. You are to use the physical properties given in the example in the text, and these properties were indicated in the problem when written on the board for you to solve. So I will show it later to you in the solution. Okay, so this is in the case of number 1. So you have your solid benzoic acid flat surface and water is flowing parallel to this flat surface. This is the temperature of water. This is the density of water. This is the length of the flat surface of solid benzoic acid. So initial concentration, let's say from 0.1 in here is 0.02948 kilogram mole per cubic meter. And then you have the diffusivity, you have the viscosity, you have the density. All of this were provided since these are the physical properties of water at the indicated temperature. So I just place it already there available for you during the quiz. So your A here is your benzoic acid and B is water. So in here, you're asked for the flux, and that's N sub A still, and your X sub BM. Now, you need to determine the Smith number and the Reynolds number in this case, all dependent on these physical properties that were provided. So in the case of the Smith number, you have your viscosity divided by the product of the density and the diffusivity. So its value is 702. For the Reynolds number, you'll be using a formula that has the L instead of the D, because you have a flat surface, so you have the length, the velocity, the density, and the viscosity. Okay, so your Reynolds number is 23,812.52. So turbulent, the flow is turbulent. And this is your J sub D. So you have 0.99 times N, your Reynolds number raised to negative 0.5, or actually it's the square root of the Reynolds number, but it should be written here below your 0.99. So that is why you have negative here. Your J sub D is 0.00648. Now this J sub D solved using your Reynolds number can be equated to this mass, specifically this K sub C prime is the convective mass transfer coefficient. This is another formula for the J sub D that you have in here. So from in here, you'll be able to get the K sub C prime. You just substitute the value. So you have 0.00648. You have the velocity. I think that's 0.152. You have the Smith number here that you previously determined, and you have the you have to raise this Smith number to 2/3. So your K sub C prime is 1.247 times 10 raised to negative 5 meters per second. You'll be needing this in the determination of the N sub A, or that's your flux. Okay? Together with the X sub BM, you need both. These are formulas available in your book. So please check whether you have an equivalent of this under the topic of mass transfer on certain geometries in your handbook. Okay, so I'll close this one now. The continuation of that is this. Now, I mentioned in the first part of the solution that you need the convective mass transfer coefficient, K sub C prime, in the determination of the flux together with X sub BM. Now, in yung X sub BM class, oftentimes, hindi siya mag-deviate sa 1.0. But I think I place it in the problem, the modified version that you have in class, that you are not to assume this to be 1. But if you did not assume it and computed for it, actually the answer is very near 1 as well. But nonetheless, how do you determine the X sub BM? The X sub BM is actually the log mean temperature difference ang formula, because you have here the X B2 minus XB1, and you have the ln here in the denominator of these two. So in order for you to know the X sub BM, which you need to substitute in here, if the problem is specific that you are not to assume its value to be 1, then you need to determine what is X sub B1 and what is X sub B2, which you need to substitute in here. So your X sub B1, X meaning it has something to do with mole fraction. So you have concentration B1 over concentration B1 plus concentration A1. Now, the concentration B1 is taken from the 996 that you have been given in the problem, I think. So if you have the first part there of the solution, please check you have the 996 there. You divide it by 18 because that has something to do with, this 18 is your molecular weight of water. This one is your naphthalene. So this is your water and this is your naphthalene. So you have the mole fraction of your water, B, okay, in your solution of water and naphthalene once your water diffused to naphthalene already. So this is your X sub B1, your 0.995. Your X sub B2, the portion in which you have the full diffusion already, you have already at 1.0. Oftentimes, this X sub B2, if you read John Cooklis, this is always assumed to be 1.0. Just like we assume that concentration and partial pressure for diffusion of, in the case of gases, it's also 0 when it is already fully diffused for the B. But in this case, it's your B is your water. So this is 1.0 already for the point B, or rather for point 2. Now, once you have already X sub B1 and X sub B2, you go back to equation 2 and substitute, and this is it. So that's the reason why if you assume it to be 1, it's okay because the answer will not matter much. But this is just a review on the formula that was covered in the first part on the topic of mass transfer, on how to account for X sub BM if it's not to be assumed to be 1.0. Now, for the dilute solution, your K sub C prime is already equal to K sub C, and the concentration of A, that is of naphthalene at 0.2, is already equal to 0, knowing that it's almost like full water because your XB2 here at 0.2 is already like 100% water because it's 1.0 in here. And another thing, the problem says that you're using a large volume of water. So your concentration of naphthalene then at 0.2 will be 0. It's like all water. So knowing the XBM, and you have determined already the K sub C prime, which could be used in lieu of K sub C for dilute solutions, then you can substitute everything here in equation 1. So this is your answer for your flux. And this is your X sub BM. There were a lot who were able to get this, but there were some who seemed lost on how to determine the X sub BM here. Okay. This formula was introduced in the first portion of what was recorded for you. Okay. Any question here? Okay, I'll close. We'll have the last part. This is for number 2 of quiz 3. So this is for a tube with an internal diameter of 6.35 mm, initial concentration of benzoic acid, which is 0.02948 kilomole per cubic meter. Water is entering this tube with this velocity at this temperature. This is the length of your tube. And the rest of these physical properties of water were provided for you. Now, I place a note here that though the length of the tube was indicated, it's only the last 1.2 meters of this tube which is coated with benzoic acid. No, not the entire length of the tube is coated with benzoic acid. So in terms of diffusion, so it's only be occurring on this last 1.2 meters, not the entire length of the tube will be used. Okay, although the problem gave you the entire length of the tube. So from once we know already from the first sample problem, which you use the same info, you already have the Smith number. At this time, you change the formula for your Reynolds number. You don't have a flat surface anymore, so you're going to use the diameter. So dV rho mu. So everything is there. You just substitute. So just convert the units to make them all dimensionally homogeneous, meaning they should agree. If it's SI, if it's in meters, all should be in meters. So your Reynolds number is 221 point, I think this is 47. So the flow is laminar, and this is your formula for such. You have here the Reynolds number, the Smith number, diameter, the length, the pi over 4. You have here the substituted values. So you have 646.15. Now, what's the use of this 646.15? I was not able to take a screenshot of the figure, but in your book by John Kuplis, if you have it, from figure 7.3-2, you are to use this 646.15. This should be your X, your abscissa, to get the Y. The Y is equivalent to this formula here that I have written. And you are to use, there are two lines in that figure. In this figure, there are two lines. You are to use the rod-like line, not the curved one, but the rod-like line. So figure 7.3-2. So this is your X, your abscissa, taken from this formula. And this should be your value for the Y. Now that Y is equivalent to CA minus CAO divided by CA1 minus CAO. Now initially we have 0A. Okay, we don't have the presence of benzoic acid. So it's 0. And you have this both 0. So you have a CA over CA1, which is 0.02948. So this is the concentration of benzoic acid in the exit part of your pipe. Pagwa na siya sa pipe. So take note that the length you use here is 1.2, not the entire length of the pipe, which is 1.82. It's only diffusion will only occur, or mass transfer will only occur on the coated part of the pipe. Okay? Yes. Sa figure 7.3-2, check ko Bob ha. Okay, that's the instruction that you're going to use the rod lock line in this case. Wait lang. Okay. Rod-like flow. What's rod? Ano ganing rod? Like flow. So it's not explained here. It was actually, I was also thinking why the rod-like flow should be followed. It's because when your water is flowing inside your tube, its shape is that comparable to that of a rod. So that is why you're going to follow this line here. If you have it there with you, if you can open it, you have to use that particular curve, which is the flow comparable to that of a rod. because the other one below is parabolic flow. So the shape of probably the eddies inside the particular geometry in which your fluid is flowing is ang iya nga shape sang flow mo is parabolic, or the characteristic is that of the eddies is comparable to that of a parabola. In this case, it's just an assumption in my case because I was not able to read the discussion here or the explanation why you have to use the rod-like flow. It's because your fluid, as it flows through your tube, is in the shape of a rod. So that is why you're going to use the rod-like flow. That's my understanding, but I don't know why it's not explained here why you are to use it.
Pero
Maybe.
for most instances, misread like aton gamiton, no?
Oo, kay isa pa,
Okay.
di ba Bob, ang flow mo laminar, so meaning not so much eddies are formed if it's laminar, so hindi siya magparabolic ang shapes ng imo fluid sa sulod. Amo na rod like siya. Laminar ni siyang flow ya eh. Kag ang ining formula nga gingamit ini siya ho para malani sa laminar flow. So if you have asked me what will we do, miss, if it's turbulent, you cannot use this particular formula anymore. The same thing with the particular, I think it's an empirical figure. Hindi mo na siya magamit kay para lang siya sa laminar. Ang sa rod-like flow. So ang parabolic sila base ilain naman na iyang formula ang iyang gamiton for parabolic flow. Okay, any questions? So wala. Sige, we go to the last, the gas absorption quiz. I will share to you the copy of your classmate because I modified the problem. So some of you will solve it differently by the others, but both solutions are acceptable. I'll share and explain later. Okay, I'll just read the problem first. You have a single problem in quiz number 4, and it talks about a gas stream from a chemical reactor which contains ammonia, and this ammonia needs to be scrubbed off with the rest of the inert gases that it's mixed with. So your mixture of gases which has ammonia is 25 mole% ammonia. So the total flow is 181.4 kilomole per hour for your tower operated at 303 Kelvin and 101.325 kilopascal pressure, where water containing 0.005 mole fraction ammonia is the scrubbing liquid. So in this case, this is not the usual case wherein your scrubbing liquid or your solvent is pure. So your scrubbing liquid in itself here has ammonia, but in a very minimal amount. The outlet gas concentration is to be 2.0 mole% ammonia. So ammonia has to be decreased from 25 mole% to 2 mole% ammonia. This equilibrium relationship, for those who have tried solving this problem, because this is written at the end of the chapter of gas absorption in Jan Kuplis, this equilibrium relationship is not given. I'm the one who placed it there. That way, you will not have to do graphical because, let's place it, your ammonia water system does not have a linear relationship in its XA and YA. So the mole fraction in the liquid and the vapor phases is not actually linear in relationship. So para masapos na hindi ka mo mangita sang slope, sang curve at the dilute end when you solve for the number of stages using Krimsor equation, I gave this to you. But there was a student, I think it was Nika, who knew, because probably she solved this problem already ahead, that there is this particular equilibrium table in appendix. Okay, let me check. So you can write it down and so you'll get acquainted. So I gave you the equilibrium equation because I was not able to tell the class that there is such equilibrium data for ammonia water system. I'm not so sure if it's available in your handbook, but you can try checking it. But in Gian Kuplis, there is table A.3-22. A.3-22 for the equilibrium data for ammonia water system. If you're acquainted with this, because you have probably practiced solving this problem ahead, you'll know that you need not use this equilibrium equation that I gave you. But for those who use the equilibrium equation and did not rely on the equilibrium table that is found in Giancouplis, it's fine. You can use this y equal to 2.53 x relationship between mole fraction in the liquid phase, which is the x, to mole fraction in the vapor, which is the y. So if you use this formula, especially in determining the minimum solvent requirement and determining the optimum number of stages, you're okay because the solution that I made is based on this. But in the case of Nika, who used the table in 8.3-22, you'll be able to see, though it's not the exact mole fraction, but I think it's just acceptable that for a 0.0201 mole fraction of ammonia in the vapor, that's YA, at a temperature of 30 degrees, which is also equivalent to 303 Kelvin, you have the equivalent mole fraction of ammonia in the liquid, which is 0.0167. So if you answered this problem using the XA here without using this particular equation, y equal to 2.53x, I'm okay with that, meaning you did practice solving ahead, and since you know where to get the value, you get it from the table. But if you have the table there with you, let me just check if it's available in Google so I can show it to you. Give me a few minutes. I think it's here, so I can show it to you. What is it? Okay. It's from Chegg. That is why it says here, ask an expert. So an expert that will work for you if you have the money. I'll look for a different table. Wait, class. Or I'll cut it here and show it to you. Okay, let me open and share it to you. Share. Can you see it? Equilibrium data for ammonia water system. Can you see it, class? I've shared it to
Yes,
you.
miss.
Okay, so this is the table that I'm referring to. Nika did not use the y equal to 2.53 equation, but she just used this data here. Although it's not 0.02 exactly, but that's acceptable, and this is the corresponding XA, the 0.0167. If you notice, class, if you have the equation y equal to mx, that's our equilibrium equation, and you'd like to determine m using this pair of values. By the way, these are values of x and y which are said to be in equilibrium with each other or at equilibrium with each other, you'll be getting an M value which is 1 point something. Now, if you use a different value randomly, you pick another one here, for example, that one, and this one, it will give you an M more or less closer to this one, but not exactly the same as the original that you have in here. And that M is not the M that I gave you because what I gave you is 2.53x. In that case, you'll only be getting an M which is 1.22, 1.20, 1.21, telling you that this relationship of X and Y for your ammonia water system is not really linear. So just that is why you have, if you have listened to the recording, you have the Henry's equation, because what Henry does is, or what Henry's law does is that it linearizes or approximates the curved behavior of the relationship of X and Y to that of a linear behavior, which is acceptable as long as you use the Henry's law constant. So if in the problem, again, I will emphasize it, you use this one, it's okay. But if there are still some of you here, wala ako lang kay Nika papel ang nauna ko, checkan nga naging gamit, yan nga table, I'm fine with that if you use this particular value. Okay? Okay, actually, these are the values, these are the pair of values of X and Y which are said to be in equilibrium with each other. But if you're going to ask me if it's the minimum solvent requirement really, if you're going to ask me, and you're to determine the minimum solvent requirement, whether it's gas absorption or stripping that we're talking about, it's always safe to go back to the solid balance in which you're using the inert streams. So what do I mean with the inert streams? The L prime and the V prime equation multiplied to not the mole fractions, but the mole ratios. Okay? From there, you'll be able to get the minimum solvent requirement. But nonetheless, you need the X for that, and you can get it from here. But for uniformity purposes class, if you don't have this table, and you are provided with an equation to use, because when you use the Crimser equation class, you need the M value that is constant. You need the M value that is constant. So what M value will you use in this case? Because your M here, if you solve it using this pair of data, will not be a constant. So it has to be the M that is provided in the problem. I hope I make sense. I will tell you later what the M is because you need it in determining the geometric mean of the absorption factor. So kung ang imo nga gingamit ining table, ang M mo di galain, so hindi na siya constant. So it's always safe to rely on the equation that is provided in the problem. My only, shall I say, I should have double checked what should be more or less the average M here. And that's the M that I reflected in the equation I provided for you. That way, no one will even think of using this table because anyhow, the M that is in the table and the M that I have provided are just the same. So I was not able to double check it in here. Okay? But nonetheless, this is the table that I'm talking about. So it's in your John Kuplis, in the appendix of John Kuplis. Okay? So you need this equilibrium equation to be able to use the Crimser equation. If you don't have this, then you can use this pair of data that should be taken from the appropriate system. So, ang ammonia water system, kung amo na ginhatag sa problem, dira ka man kwa sang X mo o kung Y, kung anong imo kinanlan, hindi ka pwede kagamit sang iya iba niya system. So, good lang kung may ara ka sini nga daan niya na photocopy or may ara ka nakatultol ka sa imuhan book nga may amo ni siya ano. Kung wala abi, so you need to go back to the equilibrium equation that is provided in the problem. Okay? So clear ko ha? And I'll close this one. I'll go back to what I was sharing to you a while ago. So in the case of this problem, you are to determine the theoretical number of stages, the minimum solvent requirement, and the optimum number of stages. In the original problem class, you were just asked to determine the minimum solvent requirement and the optimum number of stages. These are the two required information. I added this theoretical number of stages, which actually you cannot answer. You cannot answer because I did not provide you with the amount of the solvent that was used, the original amount, or the process amount of the solvent that is given in the problem. Knowing that this was copied from the chapter and problem, but the given flow rate of the solvent was not given. If you study on any books on gas absorption, you need these two information. You need the gas amount, whatever is the processed amount of gas, and what is the amount of the solvent that was used. If it's not given, if it's only one of these two that is given, at least you should have been given the, let's say, for example, the percentage recovery. That way you can connect the amount of the solute that was taken from the gas that went with your liquid. Other than that, if you go to sample problems in whichever reference books that you'll be able to have your hands on, dapat duhagi na siya given para makasolve ka sang theoretical number of stages. Why theoretical number of stages? This means that class that theoretically, given the amount of feed that is to be processed and given the amount of solvent available to take out the solute from that feed, theoretically, what is the number of stages required? So in this case, in this problem, you're only given the amount of feed, the gas feed that is processed. You are not given the solvent. So in that case, you cannot solve for letter A. So what you're going to answer is just the B and the C. So what should be corrected in your papers is just the B and the C. If you have answered A, then most probably your answer is wrong because you don't have the actual amount of solvent that was used. Okay? Now, this is our problem. I will show to you the solution to this. So this is your schematic diagram for your gas absorption process. Your gas is always introduced at the bottom. It lives at the top. Your solvent is introduced at the top, lives at the bottom. The numbering of the streams that I used is the numbering that McCabe uses. This is also the numbering that John Couples used when he is using the Crimson equation. So actually, Jan Couples uses two manners of writing the Crimson equation. It's either using only one for the bottom streams and two for the upper streams of your column, or he uses the n+1, the n, the o, and the 1 subscripts. But in my case, so as not to make things complicated, I only used 1 and 2. I label my streams below the column 1 and those streams at the top of the column 2. But the original labeling of John Couples, this should be n+1, this should be 1, this should be LO, and this is LN. Amo na yung original nga labeling, but I use this one. So in the original requirement in the problem, you are to determine the theoretical number of stages, the minimum solvent requirement, and that's the L2 in this case in my labeling, and the optimum number of stages. Your number of stages theoretically and the optimum number of stages uses the same formula. The same lang na siya. Ang naglain lang na dara ang pag-solve sa absorption factors or both, whether it's theoretical or optimum, but it uses the same formula. So in this case, if this is the formula for the theoretical number of stages, I should know the L2 and the V1. In this case, L2 is not given. So nonetheless, I determined here my inert streams. My inert streams are those streams that does not contain the solute or the component of interest that needs to be transferred to the solvent. So V prime is the representation of the inert stream for your feed gas, and L prime for your water, the pure water without the, in this case, that's ammonia. So since we do not know L2, so I just labeled it 0.995 L2. So 1 minus 0.005, meaning anything not included in the 0.005 is water. So that is why this is your L prime. So we refer to this as the inert streams. So your V prime here, in the case of ammonia, your V prime here are the other gases other than ammonia. Now, if you do overall material balance, your L2, your solvent plus your feed gas should be equal to the amount of gas that leaves your column and the amount of solvent that leaves your column as well. Now, if you use component balance using inert streams, so you have here L prime, V prime, V prime, they're all the same. The L prime here and the L prime here are the same, and this V prime and V prime here are the same. You're multiplying it with the mole ratios, not the mole fraction of ammonia on the stream that you're referring to. So in the case of this stream here, your solvent, so this is your ammonia over water. So it's mole ratio. Now in here in your V prime, so this is the stream entering. So this would be referring to this one, stream entering. So you have 136.05. This V prime is your 136.05 times this one, 0.25. So you have 0.25 divided by 1 minus 0.25. So here on the left, you have the streams entering, accounting for the presence of ammonia. And in here, you have the streams leaving. You do not know X1 in this case. X1 is not given. And you have here 0.02 for the ammonia in the leaving gas or exiting gas. So 0.02 divided by 1.02. So the right side here are for the living streams. So this is your equation 4. So notice, I intentionally write it here because I have so many unknowns. I have my L prime, I have my X1, I have my L2. So if you do ammonia, if you account for the ammonia in V2, the living gas, this one, so that should be 0.02 equal to the ammonia, which you do not know, over the inert part, the other gases, which is your V prime plus this. You actually get the ammonia in V2. So the ammonia in V1 is your 181, on the other hand, times 0.25. So it's 45.25. So look at it. This is the ammonia that leaves your column. This is the ammonia that enters in your gas mixture. So the difference of these two must be in your L1, the ammonia in your L1. It would have been possible for us to determine L2 if, or it would have been possible for us to determine the theoretical number of stages if L2 is known. But in this case, we don't have the amount of L2, even if, as I've shown in here, you did already determine the ammonia in each of the streams. So knowing the ammonia that is present here is still not enough because you don't have the ammonia actually entering to get the X sub 1 here. So the only way that you can get the X sub 1 is just like this one. No, X sub 1 is equal to 42.57, the ammonia recovered by your solvent, the difference of these two, over ammonia plus L prime, because whatever is the pure water that enters here, that is the same pure water that leaves because it's unaffected. But nonetheless, we still do not know L prime. So there's no way that you can determine the theoretical number of stages if L2 is not specified in the problem. And I missed to write that one there since I modified it. It should have been written. But nonetheless, as to the minimum solvent requirement of the optimum number of stages, you can determine it by using the equilibrium equation that I gave. So y is equal to 2.5x. So at minimum solvent, L prime minimum, you'll get the X1 maximum, or you can maximize the amount of ammonia recovered by your solvent. So that could be solved using this equilibrium relationship. So I'd like to emphasize it here, class, that if you intend to know the mole fraction of the solute in the liquid phase leaving your absorption tower, you always use the equilibrium relationship. Okay? You use the Y1 that is given in the problem, which is 0.25. This is your Y1. And the X sub 1 maximum will be determined already using the M in your equilibrium equation. So that's 0.0988. Now, where are you going to use this one? You're going to go back here and substitute 0.0988 to X1 maximum. In that case, specifically now, you're determining the L prime minimum, because the X1 that you substituted here in equation 4 is X1 maximum. So you substitute it here to get the L prime minimum. Again, I'd like to emphasize it, whether you're doing gas absorption or stripping, the X1 maximum or the Y2 maximum, in the case of stripping, should be based on the equilibrium equation. Okay? Kung ano ang provide sa problem ng equilibrium equation, you use that. Hindi man ka mo magamit graphical approach sa board exam. So, dapat tagaan yung mo sa equilibrium equation. Okay, so now that you know X1 maximum, you can go back to equation 4 and substitute it and get L prime minimum. Okay, I'll close this one and go to the next page of the solution. So if you go back to equation 4, as the 4 that was shown to you a while ago, you substitute everything. This is your minimum solvent requirement. However, class, you see this prime, this L prime minimum just refers to the water. Your solvent, remember, your solvent that enters the column is not pure water, but it has 0.005 mole fraction ammonia. So the actual amount of solvent, which is your L2 minimum, multiplied to 1 minus 0.005, where your 0.005 is its ammonia content, is this L prime minimum of 406. So the actual minimum solvent requirement, which contains 0.005 ammonia, is this. Your answer is not this one, but this one. Your answer for minimum solvent requirement would have been this if you're using pure water as the solvent. But in this case, you're not using pure water, so this is your minimum solvent requirement. Okay? Now, in getting the optimum number of stages, you need to determine the L prime optimum, which is based on what the problem specifies. If it's 50% more of the L prime minimum, which is in the case of this problem, and oftentimes it's like this, 50% more of the minimum. Okay, so your L prime optimum, if you optimize the process, is 50% more of your minimum solvent requirement. But take note, kasi it's the prime, not the actual, if you're using a solvent that is not pure. So in this case, your L prime optimum is 610.46. Now, this particular value of 610.46 should be placed in here for you to know what should be the X1 there. Because remember, the X1 maximum is for the L prime minimum. So you need to know what would be the resulting X1, the mole fraction of the solvent that leaves your absorption tower, if you're using a solvent that is optimized, or 50% more of the required minimum. So in this case, your X1 is 0.0696. This 0.0696, you subtract it from 1, you'll be able to get the L1, the actual L1. knowing the L prime optimum of 610.46, you'll be able to get now the new L1. Question is, why do we need to know, Miss Ali, the new L1? Because you have optimized the solvent that you're going to use. So there's going to be changes in the L1 there. Correspondingly, because there has been changes in the X1. So this is your new L1 if you're going to use the optimum solvent requirement. So this is your L1. Your L2 is your L prime optimum. Your L2 times 1 minus X2 will be also your L prime optimum. Your L prime optimum for whether it's in location 1 or 2 of your tower will be the same. Why? Because this doesn't change. This is the inner part of your solvent. This is the pure water. So when we talk of the solvent that enters the column, if you multiply it with 1 minus X2, which refers to the water that it contains, that should also be equal to the L prime optimum. So then your L2 will be 659.40. You need this L1 and L2 based on the change value of your solvent, which is the optimum solvent requirement in your gas absorption factor. So you have here L1 and L2. You go back to your, okay, it was shown in the first page of the solution, your overall material balance. You'll be able to get V2. Since these two change, of course, expect that your V2 is also going to change. Your V1 is the same because that's your feed. But your V2 is going to change. This one is taken from the overall material balance in the first page of the solution. So you have this. You need this for complete information, the pair of L and V's in the bottom and at the top of the column to get this gas absorption factor at the bottom, A1, and at the top of the column. Now, they are not the same. So since they are not the same, you're going to get its geometric mean, which is 1.42. And this is the geometric mean that you're going to use in the Krimser equation. Okay, so you need to have this complete. So the same thing, we go back to the first question of the theoretical number of stages. You need to have a complete set of L and V's to be able to answer the theoretical number of stages, which is totally not dependent on this, on what we are doing here. Ang ginasolve ta ni. Kaya wala na siya gasolve sa mga minimum. It's just simply asking for what is the L's, what's the V's, solve for these two A's, solve for the geometric mean of the, and go back to your Krimser equation. That will give you the theoretical number of stages. So this is now your A that should be substituted in your Krimser equation. So for the last part of the solution, so you just substitute. So this is your Y1, this is your Y2, this is the M that should be taken from the Y equal to MX equation or the equilibrium equation. And this is your X2. And this is the geometric mean of your A's. So your optimum solvent, your optimum number of stages is 6.63. In here, we don't round off to the nearest whole number. Why? Because these are all computations. So in the actual column, of course, you will have the actual numbers. But in here, since these are computation, the optimum number of stages is 6.63. The same thing when you determine for the theoretical number of stages. If it has decimal, then answer also in decimal. Don't round it off to the nearest whole number. So this is your quiz on gas absorption. I intentionally picked that problem at the end of the chapter of Gian quiz on gas absorption because actually it reviews everything concerning gas absorption except for the determination of the diameter and the height of the column. The diameter and the height of your gas absorption column. Okay, because this one simply determines the stages, what's the minimum solvent requirement, or some problems would even ask for what is the recovery, percentage recovery. And speaking of percentage recovery, you just simply account for the amount of solute that goes with your solvent. So in this case, if it's gas absorption, the amount of solute in the L1. So that amount divided by the original amount in the feed, that would be your percentage recovery. So how much of the solute present in the feed was recovered in your process. Okay? So any questions so far? You have any questions? O ay na. Why na ka mo question?
Hindi namin sa madalami sa mga determination sa mga height, ganun.
Madalagi na siya, Bob. Kaya why na siya mag-give sa quiz? So it's good that you asked about it. Most probably, if a thing has been already assessed in the quiz, for example, na-assess ko na nga kabalo ka mo mag-determine minimum solvent requirement, or na-assess ko na nga kabalo ka mo mag-determine optimum solvent requirement, hindi ko na siya pag-assess liwat. Kaya what's the purpose of assessing something na na-assess ko na? So meaning, laban-laban, ang wala ko gin-assess, amo naman na siya ang magwa. Like for example, paano ka mag-determine sa diameter ng column, sa gas absorption column? So let's say, for example, we'll discuss it now. How will you determine the diameter of the gas absorption column? If I'm going to ask you, how will you determine the diameter of the gas absorption column? You have to use the flooding correlation. It was discussed in the recording that was shared to you. You are to use the flooding correlation, which is dependent on the type of packing material that was used. You have a different flooding correlation diagram if you're using structured packing, and you have a different flooding correlation diagram if you're using random packing materials. So ina siya, diameter na siya sang column. Kung sang height naman sang column ang aton istoryahan, if it's the height of the column, amo to kay na gin-mention ko, there are 5 different ways of determining the column height, or the height of the column, the Z for a gas absorption column. Kadamo manggid kag kung tag-isa-isahon mo siya perte kalawig-lawig. So you have to choose a particular procedure that I have given kay gin-upload kuman bala ang solution ko to sa 5 ka different procedures. Kag actually may recording man ina siya. You have to choose the one that is up, shall I say, sa imo bala nga pang-insindi masapos. So let's say, for example, if you think that you're okay with the HETPN procedure, wherein the N is the theoretical number of stages, you know how to determine that already. So what remains to be determined is the HETP. So know from those particular different processes kung ano mag-determine sa HETP. What is the HETP? The height equivalent to 1 theoretical plate. And that is used in the case of gas absorption towers in which you're not using trays but rather you're using packing materials. So amo na may HETP kitang ginatawag, ano kataas ang packing material nga ma-consider mo isa na siya ka-plate if you're using a plate or a tray in your column. So something like that. So it's really very important that you know how to design your column. So that is why you need to study how to determine the diameter and the height of your column. The process is tedious. Yes, the process is tedious. So probably I would just ask one of the two, but you have to know that because that's where your design is. If you're going to ask me, your exam is more or less on design. Because the engineer ka mo dapat kabalo ka mo mag-design sa inyong equipment. So kung design na aton istoryahan, si dapat kabalo ka mag-design sa imo crystallizer, kabalo ka mag-design sa imo dryer, kabalo ka mag-design sa imo ano pa ang topic ta sa end term. crystallizer, dryer, gas absorption tower, something like that. The rest will just be, of course, the usual material balance or the use of some empirical equations together with the material balance equation. Anyway, so as I'm saying, anyway, you can open your handbook during the exam. And as to tables that you will be using, formulas that you will be using during the exam, I will have it all provided for you. So if I think it's not available in your handbook and it would be best for you to have something to refer on nga gin-print ko na nga daan, gin-pa-risograph ko na nga daan, then it will be risograph for you. Ang dalon nyo na lang gidya sa exam ang inyo handbook. Amo lang kinaing dalon nyo. That you can use. The rest will be provided by me. If there are information you think are missing and di maginaya malikawan niya, especially mga unit ops nga exam, you can always ask me. Kay miski sa una kanday Doc Feli panayaga tulo sa new ya kung sino pa na ang mga teacher, may ma-missed out na nga data, ang teacher man ang ga-provide. Sa una ang practice gidya gani class is ginabutan nga lang na isa ka handbook sa tubangan sa klase. Students are using that just one handbook. They're not really required to bring their own handbook. And since you have your handbook, some of you have your handbook, then you can bring it with you and use it during the exam. That's it. Everything that you'll be using, feeling nyo kulang manimisali ang information, wala man di ang formula, because I'm not expecting you to memorize all the formula, of course. Wala mo ko ga-expect nga memorize nyo tanay nga formula, kay mag-quiz may ara, mangani ka mo mga hawig, di ba? So I'll be the one to provide it for you. Should you need it, just tell me that you need the formula for this and this, I'll give it to you. Just the only thing that you can bring is your handbook during the exam. If I need to write on the board all the formulas that you'll be needing, if you think I need the formula for this, I'll write it on the board for you. I need the data for this, it's not in the handbook, which is unlikely, then I'll give it to you. But in terms of data, it's really available in your handbook. So the unit operation processes that you need to study is crystallization, gas absorption, drying, and the mass transfer. Mass transfer, which covers diffusion. Is there anything that you'd like to ask from me? Your exam, what's your exam? Let me check. We were emailed by the schedule of exams of all year levels. So I know your end term schedule, exam schedule. So let me see your schedule and it's there. So, sige. Thursday pa kita. So as I've said, I already clarified with register why is it that the indicated time for the exam is 7:30 to 9:30 only. So that the room, which is MM11, is available until 11:30. If you think you can finish it in 3 hours, I will be happy, so fine with me. But if you think you need more time, then we'll stay there until 11:30. MM11, 7:30 to 11:30 on Thursday next week. Do you think you don't need anymore a third quiz in the drying topic? You think you'll be okay with seeing drying problems straight in the exam? Wala na lang ta quiz? What do you think? Or do you think the scores that you'll be having in your quizzes, which I will return really on Tuesday, January 3. So you'll see your papers. Will suffice and then you'll be okay? Then we will not have a third quiz. You can have your drying problem for the first time during the exam. But it really depends on you. What do you think?
If mag-quiz, miss, mga when, miss, how? Before exam, miss?
Nag-ask pa ako room sa register kaya sila ang naga-control bala sang rooms, wala pa reply kung saan o. Pero initially ginbutang ko siya, di ko ginsalat, wait lang kita Lisa. Ginbutang ko siya of course before sa Thursday. Kaya para di may idea ka mga ay mo ni drying. Ito siya. Di ko makita ang folder ko. Where is it? Majority of you are, hindi majority, but majority gali sakto, majority sakto akong term. Majority of you really needs to make good in the CLE and in the exam because the quiz are not really good. Anyway, you'll see your paper on Tuesday. So I asked the registrar, galing Tuesday siya dayon. Tuesday, 1:30 to 3:30. Wala pa ko reply. I asked for a room on Tuesday, 1:30 to 3:30 for your quiz number 5. Although in terms of quizzes, sufficient na gintaya in terms of quizzes. And there are some of you nga, okay naman gid sila ya actually sa quizzes lang yung 4. Iti kung i-average, kung malang equivalent, okay man. Galing kay majority gid hindi okay. So amo na nga kung damuon ko quiz, mas advantageous sa majority. Pero kung if you find it already very tiring and tedious nga sige mahatag pa ko quiz 5 nga 4 naman inyo quizzes, then we'll not have the 5th quiz. Amo na lang to.